This video will discuss how characters in strings can be preserved in computer memory and the various encodings which are involved in order for us to be able to send strings across the internet. If you're interested in seeing more videos like this, please subscribe to our channel. Let us spend some time trying to understand a bit better character encoding in JavaScript. As we've mentioned before, a string is a sequence of characters. So if we have the name John, it would be represented by 4 characters, which are sequentially preserved in memory. But as far as the computer is concerned, what computers really like to work with are binary numbers. So computers are very efficient at dealing with numbers, and they don't really have a way of specifically dealing with strings and with characters. Which is why we actually have to take our initial characters, which make up the string, and somehow convert them into another storage type in memory. To do this, we have to in fact go through a couple of steps, which involve a convention. A convention in this case is a way of doing something so that everybody agrees on what the initial input is and what the output would be. And the first convention would have to be how to convert characters into numbers so that each character that we use ends up being converted to the same number. And then the second convention would be how to in fact encode these numbers into bits and bytes. For example, in the first step, we very often use the Unicode standard. The Unicode standard currently has over 140,000 characters as a part of it. And in the second step, we very often use different standards, but the UTF-8 standard is quite widely used across the internet. UTF-16 is in fact the standard which is internally used inside JavaScript. Let us go through an example. Imagine that we have our old string, John, and we will then use the Unicode standard to see how we can represent the 4 characters in John and convert them into specific numbers which we can then use. Now on the right hand side we see what is named as the ASCII standard. So this is a node standard for relating characters to numbers. The Unicode standard uses exactly the same numbers right at the beginning of its definitions. So the first 127 characters in Unicode are the same as the ASCII characters. So let us see how we can represent the name John in both ASCII and Unicode. Well, what we will do in this case is we need to find the letters. So we have capital J, we have small letter O, H and N, and as we can see, all of these letters correspond to a number. So the letter J would correspond to 74, O would correspond to 111, H would correspond to 104, and then N would correspond to 110. So notice all the standard is doing is assign characters to numbers. We would be making an additional step to convert a character number to encoded bits and bytes in memory. We have all agreed on a way in which we can use the same standard, the Unicode standard, to represent a character as a number. Let us now discuss the next step that we need to do, which is to agree on a way in which we can convert a number into strings of bits and bytes that can be recorded in computer memory. To do this, we will start off with the simplest possible scenario where we deal with numbers which can be described in a single byte, so in 8 bits of data. We would use our old examples where we use the name John, we converted it to numbers 74, 111, 104 and 110. And we will specifically focus on the first character in this case, capital J, which corresponds to the number 74 based on the Unicode standard. So the next thing that we need to do is figure out a way of how can we record this number 74 into something that uses only bits, zeros and ones. And to do this, we would use binary data. And more specifically, binary data which is recorded based on this UTF-8 standard. Well, a long time ago, people figured out a way that you can efficiently describe decimal numbers into binaries by taking numbers with base 2 and raising them to different powers. So for example, if you take 2 to the power of 0, this would be equivalent to 1. If you take 2 to the power of 1, this would be equivalent to 2. If you take 2 to the power of 2, this would be equivalent to 4. 2 to the power of 3 would be equivalent to 8. 2 to the power of 4 would be equivalent to 16. You get the drift. 2 to the power of 5 would be equivalent to 32. And 2 to the power of 6 would be equivalent to 64. So it turns out that one way of describing the decimal number 74 in binary is to figure out which of these numbers you can use so that if you add them up, you end up with 74. One thing you may have noticed is that we never use the very first bit of the 8 bits which are available to us on the left. Well, it turns out that this bit is reserved. It always contains 0 if we are describing a character by a single byte of data. One thing that we would learn a bit later on is that using the UTF-8 standard, we can describe characters by multiple bytes of data if this is required. And we would often be using these initial bits on the left-hand side so that we tell the computer that we are talking about linked bytes which should be looked at together. To understand how decimal numbers fit into binary data, one metaphor that I like thinking about is how we can fill a hole by different sizes of rectangles. In this case, we have rectangles which correspond in width to 74, 32, 16, 8, 4, 2, and 1. So one thing that we can envision is how can we in fact infill the hole which is found below, which is 74 units wide by these rectangles. So what we can do is we can check whether a given rectangle fits in the hole. If it does, we keep it there. If it doesn't, we don't. So the 64 rectangle did, so we would put in 1 in its place. We would then try the same with 32, which doesn't fit. We would put in 0. We will try the same with 16. It doesn't fit again. We would again put in 0. We will try it again the same with 8. It does fit, so in this case we put in 1 again. We try it with 4. It doesn't fit. We put in what? 0. We try 2. It does fit. We put in 1. And 1 in this case, because we have already infilled the hole, would contain 0. So this is very similar to what we will be doing with binary numbers when we want to represent a decimal number. Now let us view the same thing viewed in the standard way. In this case, we have a number of empty boxes which we will be filling up with zeros and ones, trying to figure out how to represent the number 72. So we will do something very similar. We will start off with the question is, starting from the left, is 64 less than 74? Yes, it is. So we will put in 1. We will then ask ourselves, is 32 plus 64 greater than 74? If it is, we will put in 0. We will do the same with 16. So is 64 plus 16 greater than 74? It is again a greater number, so we would again put in 0. Is 64 plus 8 greater than 74? In this case, it is not, so we would put in a 1. So we keep doing this, and we end up getting the needed binary notation. So if you're interested in a binary number, this is how you get it. So the number 10011010 corresponds to the decimal number 74. So notice the letter J was represented by this stream of 7 binary numbers with that 0 in front of it. So this is 1 byte of data. So we can think of the letter J corresponding to these numbers. So all we need to do now to describe the entire string, the name John, is to do the same for the other characters. Now it turns out that all of these characters would be defined quite nicely into a single byte of data. So in all cases, what we are doing is we are recording these streams of zeros and ones, putting them together, which would give us an entire string, ending up with the entire name John. So it turns out that there is a limit of how many characters we can in fact encode in a single byte of data. And the limit is quite straightforward. All we need to do is we need to use a binary number where all numbers are ones. which in this case would give us an addition of all of the corresponding decimal numbers for a total of 127 possible scenarios. Well, this 127 character set is in fact what the initial ASCII standard was based on, where we had some initial instructions, numbers, Latin characters, commonly used characters, and this was all that was available to us. But you can imagine that there is a need for us to describe a lot more characters, different alphabets, etc. So this is why the UTF standard has been widely adopted. It involves a very elegant way of describing almost an unlimited number of characters by making the individual bytes communicate with one another. How do we do that? Well, it turns out that if you want to use more than one byte of data, all you can do is to start each byte with a predefined set of numbers. For example, the first byte will start with 110, and the second byte will start with 10, and this will tell the computer that those two bytes are in fact linked. Now, what we then do is we would use the empty unused bytes to start recording our binary numbers. And in this case, we have 11 of these available to us. So we can use 2 to the 0, to the power of 1, 2 to the power of 2, etc. We will jump to the second byte because the two bytes are again linked. So we will have 2 to the power of 6 already belonging in the other byte, getting us all the way up to 2 to the power of 10. So in this case, we have 11 different bits available to us, making the whole possible set of characters a lot bigger. And in fact, we have 2047 of these. So we have 2047 possible characters we can encode with 2 bytes, which is very neat. But again, the real world actually involves a lot more alphabets and emojis and things like that. So we can very easily go to 3 bytes if we like to. In this case, we go all the way up to 2 to the power of 15 for a total of over 65,000 possible characters. Or if we go to an encoding with 4 bytes, we can go to over 1 million possible characters. So notice that in all cases, all we are doing is we have a standard notation where the first byte contains a number of ones followed by a 0, which is telling us how many bytes of data we are following. So the number of ones is telling us how many bytes would go together, and each successive byte would start off with 10. This is very neat because even if we end up starting at a random location inside of a stream of bytes, as long as we see a 1 and a 0 in the beginning of a byte, we would know that we are in the middle of a character, and all we need to do then is go back to the beginning and we can piece everything together so that we can start understanding how the encoding works, which is very powerful. Let us go through a 2-byte encoding example of the Greek small letter sigma. So the Greek small letter sigma, in terms of a decimal number in the Unicode standard, is represented by the number 963. So how can we represent 963 using 2 bytes of data? As we previously discussed, both of these 2 bytes of data would have some bits right in the beginning of them, which are telling us that we are dealing with 2 linked bytes of data. As we also discussed, we would be using the remainder of the empty bits to describe the number. So if we want to describe 963, all we need to do is to figure out which of these decimal numbers corresponding to 2 to different powers add up to this number, which is quite straightforward to do, as we have previously discussed, giving us the following solution. So in this case, we would have a 0, we would have 4 ones in the first byte. In the second byte, we would have 4 zeros followed by 2 ones. So this is all we need to do.